everybody, welcome back to chemistry. And so now we're moving into a new chapter, chapter 6, which is entitled thermochemistry. And so what this chapter covers is sort of the relationship between energy and chemicals. So just to give you sort of an idea of what we're going to be looking at, so imagine you have a beaker, and in this beaker you have a lot of a particular molecule. We'll call it molecule A. And so let's say molecule A has a certain mass and it has very specific properties. And then let's say molecule A may undergo a chemical reaction. And maybe the way it does that is it reacts with molecules in the air. And so A becomes a new molecule and undergoes a chemical reaction and becomes a new molecule B. So B may have a different mass and it'll probably have completely different properties. So this is sort of how we've been looking at chemical reactions in the past, but there's sort of another factor we have to look at. We also have to look at the energy of the molecules in the reaction, in particular maybe A and B. So for example, A, you can quantify its energy. Maybe it'll have something like 100 units of energy. And so it undergoes its chemical reaction, becomes molecule B, but B may not have 100 units of energy. It's a different molecule, and so it will have a different amount of energy. It may be something like down to 20 units of energy. So we're going from molecule A, which had 100 units of energy, to molecule B now that only has 20. And so that chemical reaction, you have to lose 80 units of energy. So that happens in chemical reactions. You'll have chemical reactions that release energy into the environment, and they're called exothermic reactions. We'll talk about them. Now, another possibility, let's say you have a chemical C that has a certain amount of energy, say 30 units, and it's reacting and becoming chemical D, and it has a certain amount of energy, say 50 units. And so there, in order for C to become D, it must absorb 20 units of energy from the environment to undergo that chemical reaction. So we're sort of looking at the relationship of energy with matter in a couple of ways. One way we're looking at it is we're looking at different molecules and trying to figure out how much energy they have. And another thing we're going to be looking at more importantly is the amount of energy that these chemical reactions going from one molecule to another release into the environment or absorb into the environment. Okay, so let's talk a little bit about what energy is. And so you know that there are hot objects and cold objects. And so as you might expect, hot objects have more energy and cold objects have less energy. That is a fact. But what is energy? So before the year 1800, people actually thought that energy was actually little atoms. These little atoms were of a particular element called caloric. And so it was thought that hot objects had more of these caloric atoms than cold objects. And so that was thought up to about 1800, and then people sort of figured out that that was probably not what's going on, in part because we know that things that are hot and things that are cold have exactly the same mass. And so we're not really having any kind of mass being added into a hot object compared to a cold object. So we now see energy as something a little bit different. It is not really a specific kind of atom. That's completely wrong. Rather, what energy is it's found in all atoms and molecules by virtue of the atoms and molecules' composition and their motion. All atoms and molecules have energy. So we'll talk a little bit more about that in a minute. Another thing we need to sort of discuss is it's also defined in a certain way. And so the way we define energy as the capacity to do work or the capacity to transfer heat. So let me talk a little bit about those two things. So let's say you have a dam, and behind the dam you have tons of water. And so we would say that that water has energy. And so one of the reasons why that water has energy, because it has the capacity to do work. So let me explain. So that water is sitting back behind the dam. It may not be doing a lot of work at the moment, but you know that if the dam breaks, it will flood the valley below, and that water will do work on the houses below by destroying the houses below. So you can see that energy can be defined as the capacity to do work. It also is defined also as work in itself, but it's also the capacity to do work as I just described. Also, energy is the capacity to transfer heat. So let's say you have a brick that is super hot. And so that brick has a lot of energy. That is a fact. Now, is it transferring heat if you're in a vacuum? No, it would not be transferring heat if you were in a vacuum. However, if you put a cold brick right next to the hot brick, then the hot brick could transfer energy into the cold brick. And if that is the case, that is transferring of the energy is called heat. And so you can see a hot brick has energy because it has the capacity to transfer heat into colder objects. But heat of in itself is also energy. We'll talk a little bit more about that later. Okay, so now what I want to do is sort of break down the various categories of energy. And so one category of energy which is important is breaking it down in terms of kinetic energy versus potential energy. So I'm going to talk about these two things, but sort of in the context like if you were in a physics class. So kinetic energy is actually pretty easy to understand. Any object that has mass and has motion has kinetic energy. And the reason for that is kinetic energy can be evaluated pretty easily. Kinetic energy is equal to 1/2 times the mass of the object times the velocity of the object squared. And so what you can see is if mass was 0, there would be no kinetic energy. But importantly, if you have an object with mass, but it has no velocity, velocity is 0, it's not moving, then the kinetic energy is 0. And the more mass or the more velocity that object has, the greater the kinetic energy it will have. So kinetic energy is energy that some kind of matter possesses because it has mass and it has motion. But again, keep in mind, if it's not moving, it doesn't have any kinetic energy. Move on now to potential energy. What is that? So objects also can have potential energy due to their position. So let me give you an example of this. So we have a pen here. And so this pen is a certain distance above the ground. And in physics class, you would describe this pen as, although not having kinetic energy because it is not moving, it is having potential energy because it's a certain distance above the ground. So how do we know that this pen actually has potential energy? And so there's a simple test we can do to check this out. What we can do is simply see if we let go of this pen, can we convert some of this potential energy, this energy that this pen has due to the fact that it's a certain place above the ground, to kinetic energy. And it looks like we can. It looks like you can convert potential energy into kinetic energy. So that's a clue that that pen had energy due to its position because it was able to be converted into motion, kinetic energy. Now if we had the pen even further up, it would have more potential energy. It would have a higher value of potential energy. How do we know that? Well, from the higher position, it would travel, when it got to the ground, it'd be going faster and having more kinetic energy than the pen that I let go from this position. So potential energies in physics class is usually the energy that is evaluated due to some kind of mass's position in space. So let's talk about these two examples here. We're going to evaluate these fun pictures here and try to figure out when the object here has kinetic energy and when it has potential energy. So we're going to go over here to this picture here. So let's look at the left side. And what we have here is a person swinging a pendulum. And so the way the pendulum was made was they had a washer and it's attached to the string. And this person is just swinging this pendulum back and forth. So it's here. And so now if you can imagine this pendulum moving, what you can imagine is this. When this washer at the end of the pendulum is as high as it can go, as you kind of know, then this washer is motionless. And so if it's motionless, then velocity is 0, and so kinetic energy would be 0. So here in this position, kinetic energy is going to be 0. Now, let's look at the washer when it's in the middle position. So in the middle position, you can imagine that this washer is going as fast as it can go. So here in the middle position here, as it is in the bottom of its cycle here, the kinetic energy is relatively high. Now here, when it gets back to the other side, the kinetic energy is 0 again because it's motionless. So what you can see is in this pendulum cycle, we have the kinetic energy varying from nothing when it's not moving. When it's in the middle of the cycle, it's going as fast as it can, so the kinetic energy there at that point is high. And then up here on the other side, when it's not moving, again, the kinetic energy is 0. Okay, so now we can also evaluate this washer of the pendulum in terms of its potential energy. Here, let's look at the washer again on the left, which is at its highest position. Here is furthest away from the ground. It's furthest away from the gravity source. So it's going to have relatively high potential energy. But in the middle of its cycle, when it has the highest kinetic energy possible, it's going to have a relatively low potential energy, because here in this position the washer is closer to the ground, and then when it goes up to the other end of its cycle, when the kinetic energy is 0, the washer is as high as it can go, and so its potential energy is going to be relatively high. Now, one thing you may have noticed is that as the kinetic energy is going from 0 to high, as it's going to the midpoint of its cycle, the potential energy is going from high to low. And so essentially what you can see is you're having one form of energy, the potential energy, being converted to another form of energy, which is the kinetic energy. And so this is what you see quite a bit in matter. You have different forms of energy being converted from one form to another. Okay, so let's look at this roller coaster track and figure out where the car will have the highest amount of kinetic energy and the lowest amount of kinetic energy. Well, if you know anything about roller coasters, it looks like when it gets to the top here, right before you're about to go down, here you're going to have relatively low kinetic energy for the car on the roller coaster, right? And the reason why I say that is because I know the car will be moving a little bit, so it's going to have some kinetic energy, but as you get down to the bottom of this track, it'll be moving faster and faster and faster, and maybe at this point here, it might have the highest kinetic energy. And the reason is it's so high there is, again, because the car is moving very fast, and k is equal to 1/2 mv squared, so v is a very high number, so k should be a very high number. Okay, so let's evaluate potential energy. Well, the car here, when it's highest from the ground, is going to have the highest potential energy, and when it's closest to the ground, it's going to have the lowest potential energy. And again, you sort of see an example here in a piece of matter where you have potential energy of that matter being converted to kinetic energy. Okay, so let's move on. So this is kinetic and potential energy as maybe taught in physical classes, but we're in a chemistry class, so let's talk about how kinetic and potential energy are applied in a chemistry class. Now, in chemistry, you're dealing with atoms and molecules. So the question is, can atoms and molecules have kinetic energy? And the answer is yes. And the reason is, atoms and molecules have mass, albeit it's a very small one, and they're also moving around. So each little atom or molecule has some amount of kinetic energy. You can actually calculate the value of the kinetic energy it has is equal to 1/2 mv squared. Okay, so a simple example of that. So imagine you have a solid, and let's say you're looking at the solid at a cold temperature and again at a hot temperature. So the question is, does this solid in the cold or the hot temperature, does it have kinetic energy? And the answer is yes. It's because both in the cold and hot solid, the atoms or molecules in the solid are moving. So they're not moving around each other, but the atoms or molecules are in a fixed position, but they're vibrating back and forth. And they're vibrating back and forth. That means they're going to have a little bit of movement, and they're going to have a little bit of kinetic energy. Now, if you heat the cold solid to the hot solid, what will happen is that the atoms or molecules will start vibrating even faster. And so they will have more kinetic energy, and it's for that reason that they have a higher temperature. So we can sort of see that solids definitely have kinetic energy, and so this would also apply to liquids and gases as well. And so liquids are similar to solids in that the molecules or the atoms are very close together. It's just that they're moving around each other. And they're probably going to have more kinetic energy than found in a solid usually. Now, with gases, they have tremendous amounts of kinetic energy. And the reason is, in gases, the individual atoms or molecules are moving very, very fast. And so that gives them a lot of kinetic energy. So what you can see is most certainly chemicals can have kinetic energy because they're moving around. Okay, so importantly, chemicals, say molecules and atoms, have potential energy due to their particular composition. This is a very important point. So here the point I'm trying to make here is that importantly, different molecules have different levels of energy. So let me explain a great example of that. Let's say that you have glucose. Glucose is a molecule which has 6 carbon atoms attached to 12 hydrogen atoms and 6 oxygen atoms. And so all food has glucose in it, and we can utilize glucose as a source of energy. And the reason is because glucose, the molecules themselves, are loaded with energy. And there's something about the combination of carbon, hydrogen, oxygen, and the way the atoms are bonded together that gives this molecule tons of energy. And oxygen, which will react with the glucose in your cells, has a lot of energy as well. Now, what's interesting is your cells will take the glucose, will react with the oxygen, and they'll produce 2 new molecules that they are carbon dioxide and water. But the thing is, carbon dioxide and water have less energy than glucose and oxygen. So you can sort of see this diagrammed here. And so here on the y-axis, we have increasing amounts of energy. And then on the x-axis, we have the different kinds of molecules. And you can sort of see here on the left side, the reactants here, we have glucose and oxygen, which will get into the cell. And so they have relatively high amounts of energy. But carbon dioxide and water, due to their unique structures and the way the atoms are bound together, they have relatively low amounts of energy. And so the point here to see is that molecules have different levels of energy. Glucose, because of its structure, just happens to have a lot more energy than carbon dioxide and water. So remarkably, we can use this to great effect in our cells. So our cells generate energy, and they pretty much do that through this reaction. They take advantage of the fact that glucose and oxygen entering your cells have relatively high amounts of energy, but carbon dioxide and water, the waste products from glucose and oxygen, have relatively low amounts of energy, and so the excess energy that cannot be contained in carbon dioxide and water is released into the cell. So the cell will heat up to small degrees, but usually that energy is locked in other chemicals in the cell and is utilized later. One of the major chemicals that energy that will be locked into is a molecule called adenosine triphosphate, and you'll learn about that in biochemistry. Okay. So we can classify energy in terms of the 2 types of potential energy and kinetic energy, but another important classification of energy is from where it originates. So let me go through some important examples of this. And so, for example, if energy is found in chemicals due to their particular composition that they have, this is called chemical energy. So this is energy due to the structure of the atoms in the molecules and the arrangement of the atoms in the molecules in space. And so you will have particular kinds of atoms and particular kinds of arrangements and particular kinds of bonds between the atoms and the molecule that will render that molecule to have relatively high amounts of chemical energy. But then there are other molecules that aren't so lucky, and they won't have the kinds of atoms and the configurations, and so they will have relatively low amounts of energy. But that chemical energy in those molecules is potential energy. It's not so much kinetic energy. Thermal energy is another important one. So when you have a beaker of hot water in your hand, you are feeling thermal energy. Thermal energy is the energy associated with objects that are hot. Now, what makes the objects hot? So one of the things you may have sort of seen already, things are hot because they have a lot of motion. And if they have a lot of motion, it's because they have a lot of kinetic energy. So thermal energy, again, is associated with hot objects. Things that are hot have a lot of thermal energy. Things that are cold have relatively little thermal energy. There is also mechanical energy. This is energy associated, usually seen in large mechanical devices, such as, for example, pistons or bricks or things like that. So if you have a piston moving in a cylinder, its movement is going to go through a cycle. So you'll have alternating potential and kinetic energy in that cycle. But overall, that energy would be considered mechanical energy. And then a final type of energy is electrical energy, because this originates from the movement of electrons in wires, and so this would be electricity. And so this electricity can do work, as you probably know. It is a form of energy, so it is considered both potential energy and kinetic energy. Okay, so now I want to do is talk about the law of conservation of energy. So to introduce that, let me compare it to the law of conservation of mass. So one of the things you learned earlier is that for all chemical reactions, you have as much mass going into the reaction as you have going out of the reaction. And there should be no more mass or no less mass. So this is actually also true for energy. When you have a chemical reaction, you will have as much energy going into the reaction as leaving the reaction. You can have no more or no less. And so this is called the law of conservation of energy. So all chemical reactions and processes must obey the law of conservation of energy. Now, importantly, when you have some kind of reaction or process, although you must have as much energy coming out of that process as you have going in, you can change the form of the energy. So let me give you sort of an example of that, which is kind of an interesting example. So let's say you're looking at your car and you're considering the engine in your car, and you know that the engine receives a form of chemical energy. This chemical energy is gasoline. And so here I have sort of a picture here, sort of a diagram of what's going to happen. So let me sort of draw in here an engine here, and just to indicate here all this yellow energy going into the engine is chemical energy. And so this is the energy that is found in gasoline molecules. Now what the engine will convert the chemical energy into new forms of energy that are more useful. And so one of the forms of energy that's converted to is to mechanical energy. And so that allows the wheels to turn. Now interestingly, not all of the chemical energy that's going in the engine will be converted into mechanical energy. It's only a small fraction of it, say 25%. But the other 75% is released from the engine as well. And there, that energy goes into thermal energy. And so it could be the energy is going to heating up the gas product molecules that are released when the gasoline is reacted in the engine. So that would be here, that'd be about 40% of the energy. Some of the thermal energy is being received by the coolant that the energy receives to cool down the engine. And then some of a small fraction of the energy, the thermal energy, actually is going to friction of the tires wearing against the ground. So what you can see is the engine, it can only take a small fraction of that 100% of chemical energy that's being added to it and only convert it to 25% mechanical energy. But here's the thing, despite that, all the energy that went into the engine can be accounted for. It is all going out. It's just that only 25% of it went to mechanical energy. The rest of the 75% went to thermal energy down here. So this is a perfect, wonderful example of the law of conservation of energy. Okay, so now we need to talk a little bit more about how we go about figuring out how energy is transferred from one object to another and how we go about measuring that amount. And so what chemists like to do to help us understand this is to look at something and define something called a system. So I need to talk about that. So a system is something that you define as you wish. So let me give you an example of a system. So let's say you have some chemicals in a flask here. And so here the chemicals are blue here. And so you can say the blue chemicals in the flask, you can just arbitrarily define that as a system. Now, you can define systems in other fields. For example, what you can do is you can define a system maybe more mechanical in nature. So for example, if you have a furnace in your home, the furnace in and of itself would be a system. Or for example, what you can do is maybe something biological. Let's say you have, you're looking at a particular muscle in your body, your bicep. You can sort of arbitrarily define the bicep as the system. Now, what are the surroundings? Well, when you're looking at a particular system, the surroundings are everything outside of the system. So when we're looking at this example here of the flask with the chemicals are the system, and everything outside of those chemicals, it would be sort of the surrounding air there. Those would be the surroundings. So for example, when we go back to the mechanical system of the furnace, then everything outside of the furnace, your entire house would be the surroundings. If you're looking at your bicep as the system, and then everything outside the bicep will be the surroundings. Now, usually you can also arbitrarily define a boundary to separate the system from the surroundings. And here we actually have a flask here that is sort of a useful boundary in this case. And the final thing, a final term that you need to know is you need to know what the universe is. What the universe is just the system and surroundings all together. So we have sort of a nice description of the system and surroundings in this picture here. So in this leftmost box here, what we have is a system of chemicals which is in blue here, and everything outside of that in gray is the surroundings. In this middle picture here, the surroundings are now in blue and the system is in gray. But when you add the system and the surroundings together, everything, that will give you the universe. Okay, so the reason why we define a system and its surroundings is because that is a way we can figure out how much energy is being transferred from the system to the surroundings, or maybe from the surroundings to the system. So let me talk about how we sort of analyze this. So let's imagine again our system. And so our system here is going to be these blue chemicals here in the flask. And so let's say we were able to somehow evaluate the total amount of energy in the system here. And so here we sort of have maybe a gauge to measure the energy in our system, in our blue chemicals here. And so they're up to this point here. And then also maybe what we're also doing is we're somehow able to measure the energy outside of the system. We're able to measure the energy in the surroundings. And so here is the energy gauge for the surroundings, and what you can see is that the energy of the surroundings may be less in this example. So let's say we carry out some kind of reaction in the system. We carry out some kind of chemical change in the system. And let's just sort of imagine that during this chemical change, energy is leaving the system and going into the surroundings. Now, after that chemical reaction is finished, let's evaluate the amount of energy in the system and the surroundings now. Well, if energy left the system, after this transfer of energy, now you can see that the system has lost energy. But importantly, any energy that was lost by the system has been gained by the surroundings. And so you can sort of see it in particular when you look at the bars in these graphs. So here, what you can see here, with the system before the reaction, it's going to lose here this amount of energy. And you can see after the reaction, it has lost that. But look what has happened. The surroundings picked up that energy, and so they have more energy. And so what you can sort of see is that although the amount of energy in the system and the surroundings is changing during this reaction, the total amount of energy in the system and the surroundings, in other words, the total amount of energy in the universe, is constant. So this is another way of saying the law of conservation of energy, is that when you have some kind of chemical reaction occur, although you might have energy leaving the system and going to the surroundings, or maybe you have energy leaving the surroundings and going to the system, you're going to have a constant amount of energy in the universe during this process. Okay, so now this kind of slide points out that there are different definitions of systems which you need to know about. So let's say you have, your system is these chemicals, this flask here. So you can see that the flask is open. And so if you wanted to, you could add matter into the system, or maybe if you wanted to, you could take matter away. Also, you can see maybe the flask is made of glass, and so the heat can leave the system and go into the surroundings, or maybe heat can leave the surroundings and go into the system. So when you have a system which allows transfer of mass and heat with the surroundings, this is an open system. So here we have now the system here. You can see it's in its flask, but it's closed. And so you cannot transfer mass into the system, nor can you have mass leaving the system and going to the surroundings. And therefore, mass cannot leave the system. However, heat can. So when you have a system that cannot transfer mass with the surroundings, but can transfer heat, this is called a closed system. Now, in the last example on the right here, so we're kind of imagining here we have a flask in a very insulated container such that heat cannot be transferred from the container, the flask, with the surroundings. And so if that is the case, and mass can also not be transferred as well, this is called an isolated system. Another fancier word for this is an adiabatic system, but you don't really have to worry about that. We'll maybe mention that one later. So another final thing you should know about is that in general, when we're dealing with chemical reactions, what we'll find, chemical reactions will transfer energy in two ways. They will either release energy into the surroundings, or they will absorb energy into the surroundings. So let's talk about an example of a reaction that releases energy into the surroundings. So here we're looking at a chemical reaction. We'll say these chemicals are the system. And so these chemicals are here CH4, which are methane, plus oxygen, and they will react to produce the products carbon dioxide and water. And so the system is just this chemical reaction that is occurring. You may recognize this as the burning of natural gas. And so you may know as you go about burning natural gas, it's going to release energy out of this chemical reaction. It's going to release energy out of the system, and it's going to go into the environment. When you have a chemical reaction that releases energy into the environment, this is called an exothermic reaction. Now, another possibility is you can have reactions that occur which don't so much release energy in the environment, rather for them to go, they have to absorb energy from the environment. And so the way you know that is actually going on is, in particular, like if you have a solution and it's undergoing a chemical reaction, and the solution over time is getting colder, what that must mean is that that chemical reaction within the solution is absorbing energy from the water to go. And so particular reactions like that are called endothermic reactions. So an example of an endothermic reaction I have here is when you dissolve this ionic compound, ammonium nitrate, as soon as it hits the water, that compound will require energy from the water. It will absorb energy from the water in order to dissociate into its constitutive ions, which are ammonium and nitrate. And so if the water is getting colder, the environment is getting colder, that suggests that the chemical reaction is absorbing energy from the environment. And so when you have chemical reactions that absorb energy from the environment, they're endothermic reactions. Now, one more last thing I should mention. Another way you can know that you have a chemical reaction that is exothermic is if you have an equation and there's an energy term in the equation, if the energy term is on the products side of the equation, then that is an exothermic reaction. On the other hand, if the energy term is on the reactant side of the equation, that is an endothermic reaction. So with our burning of natural gas, here we have this equation here, and so it's going to be releasing energy into the environment, and so we put that energy term on the right side of the equation. So that just kind of confirms that this is an exothermic reaction. Here with the endothermic reaction, it must absorb energy from the environment to go. And so if that is the case, then we put the energy term on the left side of the equation. If you see that on the left side of the equation, that suggests that particular reaction is an endothermic reaction. Thank you for listening. We'll see you next time.